one side. Don't worry about those.
Thank you.
We can do phrenic on this one. That's this nerve coming right down past the scalenes, right here. That's phrenic. So we just can't do the brachial plexus nerves. And then next, so we skip past all the thoracic region. Next is lumbar. Lumbar plexus has nerves that innervate muscles and skin of the anterior lower limbs, lower abdomen, and genitals. If lumbar plexus takes care of anterior lower limbs, what plexus takes care of posterior lower limbs?
Lumbar.
Must be the last one, sacral. So it takes lumbar and sacral together to cover the entire lower limb, while one plexus takes care of the entire upper limb, and that is brachial. So from lumbar plexus, you only need to know femoral nerve. And to separate it from sciatic, because they're both large, sciatic is larger, it's the largest nerve. Remember that femoral passes anterior to the hip, sciatic passes posterior to the hip. So on this model, you can see both sciatic and femoral. Femoral is coming off of the lumbar plexus up here. This is femoral, right here, and right here. That's femoral. So it's coming anterior to the hip joint, and then behind the hip joint back in here, sciatic right here, and right there. So we can get all the nerves on here except the ones from the brachial plexus. Sacral plexus innervates muscles and skin of posterior lower limbs, buttocks, and genitalia. So genitalia is innervated by both lumbar and sacral plexuses. Now on this model, you can only see the sciatic, not the tibial and common fib. For that, you can use the lower limb model. And here's one that's exposed. So here's sciatic, comes all the way down, splits here. The continuation is tibial. The one that goes off to the side is common fib. And then the green board in the back we can use for femoral and sciatic and tibial and common fib. So everything for the lower limbs. Next is part 2. So everything on part 2 that's underlined, all the anatomy, is on the final as opposed to the lab exam. So we've now covered all the material for the upcoming lab exam. Homeostatic imbalances of spinal nerves. So this is more for you to work through on your own. The answer to each question is in the page numbers I've given you. But knowing what some of these nerves innervate, we could probably predict some of these consequences. For example, phrenic nerve. If the phrenic nerve is cut, completely severed, what are you going to lose control of? Diaphragm, which is the main muscle for inspiration. So breathing is going to be very difficult. Ulnar nerve. What if you sever the ulnar nerve? Which muscles would likely be affected? So is it going to be the extensors? Or is it going to be the flexors?
Flexors.
Extensors. Which nerve gets compressed by the piriformis muscle?
Sciatic.
And that results in an irritation and a general feeling of pain radiating typically all the way down the lower limb called sciatica. What if the phrenic nerve is irritated, not severed or damaged, just irritated? And this happens all the time, especially when you eat a large meal.
Hiccups.
Hiccups. Correct. Next is dermatomes. This is a map, it's sensory, showing you which regions of the skin are innervated by the different spinal nerve pairs. So if you have paresthesia coming from lower abdomen, where in the spinal cord might the problem be? It could be dorsal horns, it could be dorsal roots, it could be nerves themselves, it could even be the skin. But we need to start to narrow down the culprit. So if we're thinking nervous system, where would we look for a problem? If you have paresthesia in the lower abdomen. Upper thoracic, right? Somewhere around T10, T11, T12. What region of the cord may be damaged if you have lack of sensation from the penis? So if you look on the map, S2 and S3, sacral spinal nerve pairs, 2 and 3. So it gives the clinician a map of the body and a starting point to figure out why there's loss of sensation or abnormal sensations. But it doesn't tell you anything about motor, it's purely sensory. Motor division of the peripheral nervous system. So in part 1 of this study guide, we covered the sensory division of the peripheral nervous system. And we looked at 3 levels of processing. There was the receptor level, the circuit level, the perceptual level. Okay, those are the 3 main components of the sensory division. Motor division also has 3 levels, but completely different names, right? There's no receptors involved. There's no conscious awareness, no perception involved. In fact, now we're actually starting at the cerebral cortex, and we're working our way down to the skeletal muscle. If it's somatic, if it's autonomic, we're starting in brainstem nuclei or hypothalamus and going down to peripheral targets like smooth muscle or cardiac muscle or glands. Right, so we've got the peripheral nervous system here. Motor pathways means we're going from the CNS out to targets. If it's somatic, then the target is skeletal muscle. If the target's anything else, autonomic. We've looked at this a few times now, comparing somatic to autonomic. Here the red are called upper motor neurons. The black ones are called lower motor neurons. It's a 2-neuron chain to get from primary motor cortex to the muscle for voluntary direct control. You can't call these upper or lower motor neurons, but what I have said is this purple one is analogous to, it's the equivalent of this upper motor neuron, which is simply a neuron that takes you from a higher brain region, a higher brain center, to a lower brain center, or even the spinal. So a similarity, lots of similarities between here and here. If the lower motor neuron that's controlling the skeletal muscle is controlling a muscle of the head or neck, the cell body is going to be in brainstem nuclei, the axon is going to pass through cranial nerves. Same thing here. If the cell body of the preganglionic neuron is in the brainstem nuclei, then its axon is going to pass through a cranial nerve, and the target is typically associated with the head or neck. The only exception to that general rule would be the vagus. Right? Vagus is a cranial nerve. Preganglionic parasympathetic fibers pass through the vagus to reach their targets, but the vagus does go into the ventral body cavity and controls structures below the head and neck. Right? And how do we know this is parasympathetic rather than sympathetic right here? What's the anatomical nickname for the parasympathetic division?
Rest and digest.
That's the functional nickname.
How?
Craniosacral. If the preganglionic autonomic neuron is found in brainstem nuclei, it must be parasympathetic. Because where are all of the preganglionic sympathetic neurons? All of them. T1 to L2. What's the nickname of the sympathetic division? Anatomical nickname.
Thoracolumbar.
Thoracolumbar, exactly. Okay. So assuming this is thoracic or upper lumbar, this would be sympathetic. This is clearly brainstem nuclei. This must be parasympathetic. I've also mentioned in the past that these two together are the equivalent of this single lower motor neuron. In that, this lower motor neuron takes you from the CNS all the way out to the target. Here it takes two neurons to get from the CNS all the way out to the target. Back to the study guide for a moment. So under motor division of the peripheral nervous system, connects the CNS to effectors, which are mainly muscles and glands. Motor pathways have the same components of sensory pathways. Nuclei in the brain and spinal cord, tracts in the brain and spinal cord, and then peripheral nerves, spinal nerves and cranial nerves. The only difference is we're now looking at signals going from the target instead of signals going from a receptor into the CNS. But still the same basic components. For example, give me the name of the nucleus in the brain that receives somatic sensory input from the lower limbs. Nucleus gracilis. Good job. How about a nucleus in the brainstem that receives visceral sensory input? Solitary nucleus, NTS. So brainstem nuclei are involved. How about a tract in the spinal cord that carries somatic sensory information from the lower limbs up to the brainstem? Vesiculus gracilis. Somatic motor output to skeletal muscles is achieved through alpha motor neurons, also called lower motor neurons. So autonomic output to anything other than skeletal muscles, smooth muscle, cardiac muscle, glands, adipose, etc. That autonomic output requires a two-neuron chain, a pre- and a post-ganglionic, and it's the post-ganglionic that ultimately innervates the target. So here's your lightly myelinated preganglionic, it's a type B fiber. Here's your unmyelinated type C fiber, which is the postganglionic. If we were innervating the skeletal muscle, you would have branches at the end of the axon. At the end of each branch, an axon terminal. Each axon terminal would be very, very close to a motor input and would release neurotransmitter that would bind to receptors only at that motor input. Because we may want to stimulate one or a few muscle fibers in this muscle belly, but not all of them, right? Because we just need to produce a little bit of force. When it comes to smooth muscle and cardiac muscle or a gland, we stimulate all of it or none of it. There's no recruitment, no equivalency of motor unit recruitment with smooth muscle or cardiac muscle. It's all or none. So we don't have to be as precise. We don't have to be careful to make sure we only stimulate these muscle cells and not those ones over there. So rather than neuromuscular junctions, we have these swellings along the branches of the axon called varicosities. So there is no axon terminal here. Really, each one of these is the equivalent of an axon terminal because this is where the neurotransmitter is released. So it almost looks like beads, like a beaded necklace, just kind of draped over the target tissue. And when the neurotransmitter is released, rather than being very specific to a particular cell, it's just kind of sprinkled over lots of cells at once. It's almost like raining down neurotransmitter all over this tissue. If these are sympathetic neurons, postganglionic sympathetic neurons, what's the neurotransmitter they're going to secrete most of the time? Norepinephrine. What if they're parasympathetic postganglionic fibers? What are they going to secrete? learned this in chapter 11. Acetylcholine. What receptors will that acetylcholine bind to at the target, like smooth muscle, cardiac muscle?
ACH receptor.
Muscarinic ACH receptors. What's the norepinephrine going to bind to at its targets? What would you call those receptors? Old name is noradrenaline. Adrenergic receptors. And then Thursday we'll cover the two types, alpha and beta. We've already looked at the two types for acetylcholine, nicotinic and muscarinic. The origin, I think I already mentioned this, of the equivalent of the upper motor neuron for the autonomic division, it's originating either in the hypothalamus or nuclei within the brainstem, like the cardiovascular centers in the medulla, for example. Motor integration. So again, like the sensory division, the motor division has three levels. Levels of control, in this case, since we're doing motor now, we're looking at output signals. With motor, you start at the cerebral cortex, and you work your way down to the periphery, kind of the opposite direction compared to the sensory division. Now, you might think at the very top of the levels, you would have the primary motor cortex as the highest level. But remember, the cells of the primary motor cortex are the keys to the piano. If you actually want to play music, that's going to have to come from somewhere else. Premotor cortex, or motor association. So even at a higher level than the primary motor cortex, are the areas of the brain that coordinate and plan out the activity that ultimately comes from the primary motor cortex, right, through those upper motor neurons. So cerebellum, basal nuclei, premotor cortex, they all represent the pre-command level. Their job is to coordinate the output signals that ultimately come from the upper motor neurons down to the lower motor neurons. From the pre-command level, you then have projection level. This involves the primary motor cortex. Now that's for the pyramidal pathway. If we're talking extrapyramidal pathways, vestibular nucleus, red nucleus, reticular formation, tectum, right, for the extrapyramidal pathways. So if we're looking at somatic, voluntary control, it's the pyramidal system. So those upper motor neurons project down to the cell bodies of the lower motor neurons, which are in the spinal cord or brainstem nuclei if we're controlling skeletal muscles of the head. So at the level of the spinal cord, we have the segmental level. Within the segments of the spinal cord, there are networks, groups of neurons that work together as one unit called central pattern generators, CPGs. It seems like a very simple task to walk, locomotion, but think of all the muscles that are involved. All those muscles in the upper limbs for the arm swing, all those muscles in the lower limbs for the gait, all the muscles of the trunk helping you keep a balanced, upright position. All those muscles are working together. But really, we're just repeating the same thing over and over, right? Left leg, right arm, right leg, left arm, and just repeated, movement. And all you have to think is, I want to walk over there. You don't have to think about all those movements. There's a lot of reasons why that's the case, but part of it is central pattern generators. We can stimulate a network rather than individual lower motor neurons. We can just stimulate the network. And the network takes care of stimulating each and every lower motor neuron in the right sequence at the right intensity. And we've proven the existence of CPGs simply using electrodes and applying a voltage. And I've seen these experiments firsthand at UC Davis. I went went into a lab that had a cat walking on a treadmill. The cat was anesthetized. The spinal cord was exposed. There were electrodes in the spinal cord. They would apply a stimulus, a voltage, and all of a sudden, both of the upper limbs would do this. And then they would go somewhere else and stimulate another CPG, just one point within the spinal cord, and then the back limbs would do the same thing. So there's a lot of muscles working together to do this sort of motion, right? But we're just stimulating one area of the spinal cord. So we can't be hitting all the right lower motor neurons to create this movement. We must be stimulating a circuit. These circuits are built in for activities we are meant to carry out. We are meant to walk. Locomotion, we're designed for it. We have the circuits that make it very efficient.
So, Professor, obviously you can damage the circuits, but are there conditions that are like inherited through genetics that would?
Nothing congenital that I know of involving CPGs.
Okay.
I mean, it doesn't exist.
Yeah.
I'm not aware.
Okay.
Next is neural reflexes. A neural reflex should look very familiar. It's got the same components as a negative feedback loop. The difference is with a negative feedback loop, there's a problem, there's a variable that's going up or down, and we need to counter it and get it back into the normal range. With a reflex, there's not something that's too high or too low that needs to be brought back into the normal range. There's a problem and there's a solution, but you can't really call it a negative feedback. If the problem is you've stepped on or you've placed your hand onto a sharp object, the reflex is withdrawn. Right? So you could call it a pain reflex, but it's a withdrawal reflex. It's to remove your limb from the stimulus that's potentially damaging or is damaging. Something really hot or something really sharp. But the components are the same. Stimulus, sensory or afferent neuron, bringing the signals into the CNS for processing at the integration center, aka control center, which then sends output signals through efferent or motor neurons to reach the target, maybe skeletal muscle, maybe something else, which we would call the effector. Same components. If the sensory neuron directly synapses with the motor neuron, and we do see this in the stretch reflex, then you would say that reflex is monosynaptic, one synapse between sensory and motor. Aside from the stretch reflex, any other reflex is going to have at least one interneuron involved, which means at least two synapses. At the very least, you have one between sensory and interneuron, and then a second between interneuron and motor neuron. Well, that's polysynaptic. So if it's not monosynaptic, it's polysynaptic, two or more. So we have a number of different ways we can classify reflexes, and one is based on the number of synapses. So only the stretch reflex is monosynaptic. Any other reflex we look at, poly. If you're born with the reflex, if it's innate, that's going to be different than a reflex that you learn, that's acquired. The withdrawal reflex is innate. The reflex of you slamming on the brakes whenever brake lights flash in front of your car, that's learned. Right? That's happened to most of us enough times to where our reflexive response, as soon as the car in front of us hits the brakes and we see those brake lights shining, we hit our brakes. Right? Before we even really think about it, that's a learned reflex. If the reflex involves spinal nerves, as opposed to cranial nerves, it's a spinal reflex. If it does involve cranial nerves, it's a cranial reflex. You can also classify based on the target. If it's skeletal muscle, it's a somatic reflex. If the target is anything else, it's a visceral reflex. So how about the monosynaptic stretch reflex? It's monosynaptic. Is it innate or acquired? It's innate. The stretch reflex is innate. You don't learn it. Is this particular reflex spinal or cranial?
Spinal.
The one we're looking at here.
Spinal?
It must be because the muscles involved are in the lower limb, and you would use spinal nerves to innervate those muscles. So that's a spinal reflex. Is it somatic or visceral, based on what we're targeting here?
Somatic.
Somatic is its skeletal muscle. Right, so you can take any reflex and classify it a number of different ways. So we're going to go through some very specific reflexes. Stretch reflex is monosynaptic, so it's the simplest. Important for maintaining muscle tone in our extensors and our postural muscles that help us maintain body position. If you're standing, anatomical position, is it flexors or extensors that are active right now, that are keeping you in this position?
Extensors.
Extensors. All extensors. If you flex, you are moving out of anatomical position. Extension is what's putting you in anatomical position. Right? So when we talk about flexion at the elbow, we're moving out of anatomical. How do you get back? Extension at the elbow. So primarily extensors. So let's say you're standing there, and all of a sudden, after you've been standing for quite a while, your knee gives out. Quick little bend of the knee. Why do you pop right back up?
Monosynaptic reflex.
Stretch reflex. That's its job, to keep you in that body position. So if you start to deviate from it by flexing at a particular joint, maybe the hip, maybe the knee, the response is to contract the muscle that was just stretched. So you have a stretch receptor in the muscle. That's using a very simplistic term to describe it. It's a muscle spindle, but it's basically a stretch receptor. Sends signals into the CNS through the sensory neuron, directly innervates the motor neuron that goes right back out to the same muscle that was just stretched. Very, very simple. Now, even though the reflex itself is simple, the muscle spindle is not so simple. You need to understand how the muscle spindle operates. This whole thing is a muscle spindle. It consists of 4 neurons innervating what are called intrafusal muscle fibers that are wrapped in a sleeve of connective tissue. So we've cut a window into the casing of this muscle spindle so you can see inside. When we talk about muscle fibers, just regular old muscle fibers, going back to chapter 9, we're talking about these ones outside of the muscle spindle. These are called extrafusal fibers, outside of the fusel, the muscle spindle. The muscle fibers inside are called intrafusal fibers. Their job is not to contract to generate force. That's the job of extrafusal fibers. But they can contract, and they need to, to maintain the sensitivity of the muscle spindle, no matter what the muscle, no matter what our starting point is. Also, sensory neurons innervating these intrafusal muscle fibers. The primary sensory ending wraps around the middle non-contractile portion. The secondary sensory nerve ending contacts the ends of the intrafusal fiber in the contractile region. The difference between the two: primary endings can detect 2 things: change in the length of the muscle, and also the rate at which the muscle length changes. So we can tell the difference between a very quick change in muscle length or a very slow change in muscle length. Whereas the secondary nerve ending can only monitor change in length, not the rate of that change, just the absolute change in. motor neurons. So the one that we've been calling lower motor neuron, the one that controls skeletal muscle, forms neuromuscular junctions. Turns out the full name is alpha motor neuron, to distinguish it from gamma motor neuron. Alpha motor neurons control extrafusal fibers. So that's just your regular lower motor neuron with your regular muscle fiber. And then the gamma motor neurons innervate the intrafusal fibers. In order for the muscle spindle to be sensitive at any muscle length, we have to be able to not only lengthen the intrafusal fibers, which is easy, we stretch them, and that's passive, but we also have to be able to shorten them. And the only way to do that is actively, to actually contract them. So what you're going to find is alpha motor neurons and gamma motor neurons are coactive. So they signal their respective muscle fibers at the same time. Whenever alpha motor neurons become active, so do gamma that serve the muscle spindle in that same muscle. Co-activation. To understand why that's important, it helps to look at what happens if there isn't co-activation, to see what that problem would actually be. So that's the point of this slide. So on the next page of the study guide at the top, it says when a muscle belly is stretched, the intrafusal fibers and the extrafusal fibers lengthen, stimulating the muscle spindle, the sensory inputs. They find action potentials, the information comes into the CNS. It's interpreted as an increase in length, right? The muscle has been stretched. Contraction of only extrafusal fibers would cause the muscle spindle to become slack if it weren't for the contraction of intrafusal fibers. Meaning, if it wasn't for the alpha-gamma coactivation. See, coactivation allows the muscle spindles to shorten in conjunction with the extrafusal fibers, so they maintain their sensitivity at any given length. All right, so here is the muscle length. This is what we're trying to maintain. So let's say we're in a standing position. This is quadriceps. Here's the length we're trying to maintain. Here's the frequency of action potentials coming from the sensory nerve endings at this time. This is the particular frequency, which is interpreted as a particular length. So we know what the length is right now. If the length suddenly increases, what's going to happen to the frequency?
Increase.
It's going to go up, which is what allows the central nervous system to interpret as an increase in length. That's how it interprets the increased frequency as an increase in length. All right, so let's say this is our new muscle length at the moment, and then we're going to change body position, and in doing so, we need to shorten this muscle. So we're going to shorten the muscle by contracting it to achieve this new resting length. This is the new length of the muscle in this new body position that we're trying to maintain. So maybe here we were seated, and then now we're standing, which means the quadriceps had to shorten even more to fully extend the knee. Well, if only the extrafusal fibers contracted and not the intrafusal fibers, then the muscle spindle itself would become slack. So that's what the waviness is meant to show, that it's become slack. The nerve endings that wrap around the intrafusal fibers only detect something as long as that intrafusal fiber is taut. There's got to be some tension there. If you allow it to become completely loose, flaccid, lax, however you want to describe it, it's not going to read anything, right? There's no action potentials coming from the muscle spindle right now. It's not sensitive. It's not detecting anything. To avoid this problem, you have to make sure when you change your body position, when you change the muscle length, as you change body position, you have to contract the extrafusal fibers and the intrafusal fibers at the same time. So you're going from here to here. Here's our new length, but we did co-activate the alpha and gamma motor neurons, so both intrafusal fibers and extrafusal fibers contracted to the same extent. So now we're back to our original sensitivity. So this is where we're trying to keep it, and from that point on, if this muscle suddenly stretches, we'll know that because the frequency would go up. But if we suddenly stretch the muscle from this point, nothing would happen, right? At least not until we get back to a position where these fibers are taut. So again, the whole point of this slide is to show you what happens if only alpha motor neurons were activated, if you did not have the co-activation. So to summarize, you could say that co-activation is important for keeping the muscle spindle sensitive to changes in length. Patellar or knee-jerk reflex, either name, patellar reflex or knee-jerk reflex. So with most reflexes, there's more than one limb, there's more than one component. When we looked at the stretch reflex, we were looking at only the stretch reflex component of the knee-jerk reflex. I'll show you what I mean. Hit the patellar tendon, patellar ligament technically, with the rubber mallet. That stretches, very quickly stretches the quadriceps, activating the muscle spindle. Signals along the sensory fiber come into the spinal cord. Part of this pathway is a direct synapse between the sensory neuron and the motor neuron. The plus sign indicating we're activating, we're stimulating that motor neuron, which goes out to the very same muscle we just stretched. That alone is the stretch reflex. But there's more to the knee-jerk reflex than just the stretch component. A collateral comes off that sensory nerve fiber, stimulates an inhibitory interneuron. I know that it's inhibitory because of the minus sign. That's an inhibitory synapse. Well, if you're trying to contract the quadriceps, which muscle would you want to inhibit to make sure you do actually get extension of the knee? The hamstrings, the antagonists. So while we stimulate the agonist to contract through the monosynaptic reflex, we're going to use an interneuron, an inhibitory interneuron, to inhibit the antagonist. Because if you didn't do that, what might the hamstrings do or have while you're trying to perform this extension of the knee? Muscle tone, right? Muscles have muscle tone, low-level contractions all the time. So sometimes we don't even want that. If it's an antagonist, we want to completely inhibit it, so there's not even muscle tone during that movement. Because any contraction coming from the hamstrings is going to oppose what the quadriceps are trying to do. We want this to be efficient. So what was the whole point of the stretch reflex? So we can look at it from slide 53 or slide 56. They both involve the stretch reflex. What's the point? What's the function of that reflex? To maintain the current length of the muscle, to maintain the current body position. So again, if you're standing there and your knee suddenly bends, you just stretch the quads. The response is contraction of the quads to keep you in that upright position. Now we have the Golgi tendon organ reflex, or simply tendon organ reflex. The goal now is to prevent damage, to keep the muscle from generating so much force that it damages itself by tearing the muscle or the connective tissues of the muscle, or damaging the tendon, which is unlikely because it's so strong, or damaging the bone, which is more likely to happen than damaging the tendon. And that can happen. The tendon can pull so hard on the bone that it actually pulls a piece off. This is sort of like the governor of an engine, of a motor, a motorcycle or a car. Right? That motorcycle can generate more torque, more horsepower, it can go faster than the governor is allowing it to go. And what's the point of the governor? keep you from burning up that motor, right? What's the point of the governor here with muscles? To prevent them from damaging your body because they're generating too much force. So a little aside, but it's connected to this governor thing. So that's the GTO. That's the function of the GTO. It's going to constantly monitor tension from our tendons, and what creates tension is the pull of muscles on those tendons. So it's gauging muscle force, muscle output, or force output. So related to that would be weight training. So let's say you're lifting weights for the first time, doing bicep curls, you go in, you grab those nice big 10-pound dumbbells, and you do a set of 10, you're like, okay, I'm good. And then 3 days later you come in, I can do 12 now. 3 days later you come in, 15. 3 days later, 18. Man, I'm getting really big, really fast. And you look in the mirror, but I don't look any bigger. But I'm getting stronger. Well, what accounts for most of that increase in strength in those first few weeks of training? The GTO becoming less and less sensitive. Because you're performing a movement that you haven't performed before, or very seldom. And so it's kind of a shock to the system. So the body's very protective. Well, I'm not going to let you generate too much force because I don't know what might come of it, right? I don't know what kind of damage might be created. So we're going to be really sensitive, and when that tension rises, we're going to cut it off pretty quickly. But through repetition, your nervous system learns, oh, we can give you a little bit more, a little bit more, a little bit more. No problem, no damage, just kind of feeling things out. So desensitization of the GTO accounts for some of that increase in strength early on. And it often gets frustrating for people that are doing this because after they lift weights for 3-4 weeks, those increases in strength start to plateau a little bit. Now it's a lot harder to see increases in strength. But that's because now you're relying solely on hypertrophy. Any increase in strength is coming from bigger, stronger muscles, not from desensitizing the GTO. So if it's protective, what's the appropriate response for the muscle that's generating too much force? Stimulate it or inhibit it? Inhibit it. But if you go back to the stretch reflex, what was the appropriate response for the muscle that was just being stretched? Stimulate it. Right? In that case, we want the muscle to contract, but here we want it to relax. So here's the quads generating too much force detected by the GTO. Sensory signals come in through that sensory nerve fiber. It innervates neurons. So there's two legs, right? Two parts to this reflex. You have an inhibitory interneuron and an excitatory. The inhibitory interneuron is going to inhibit the lower motor neuron going to the same muscle that was just generating force. At the same time, we're going to go ahead and contract the antagonist. We're going to relieve the tension off of that tendon. So what was creating that tension was contraction of the quadriceps, which was pulling on the tendon and extending the knee in the process. So we're going to stop the extensor from contracting, and then we're going to reduce the extension by stimulating the antagonist. So we're going to get a little knee flexion. Meaning, we just want to take the tension off the tendon. That's all. So you inhibit the muscle that was creating that tension, and you stimulate the antagonist to reduce the angle.
Physiology question, but say someone like me that used to train a lot prior to biology class, but so my GTO maybe was okay with, let's say, 1,200 pounds on leg press, right? Before my hernia, but I haven't done that, you know, so did that reset along with the muscle atrophy that acquired because of that?
But
so
you
it's
know,
like,
as I do, because we've both probably gone through many cycles over the years of lifting for a while, stop for a while, lift for a while, stop for a while.
yeah.
The first time you lift and the first time you gain size and strength, it's slow.
Right.
But anytime you do it again, it's like riding a bike. You increase strength and size, I think, from my own experience, much faster when you've been there before.
Yeah.
To go beyond the point where you once were is a whole different ballgame. But just to get back to where you were, usually you can get there pretty quickly. And I'm sure a lot of it does have to do with the nervous system kind of desensitizing the GTO more quickly.
Okay,
I mean, it's been a while, but you have done it before.
yeah. So look out February.
Look
Start
out,
out at 1,200, Mike. You're
look
good.
out, December 20th.
First day the classes started this semester, I stopped playing drums and I stopped exercising.
Oh, I thought you went back to it after like 3 weeks. No?
Wanted to.
Me too. I tried.
So I've got a
Twice.
week and a half and then I'll be back on it.
Me too.
Just wait for a few weeks.
Yeah.
Okay, next. Withdrawal reflex. Function, withdrawal. Name tells you. Withdraw from something that's potentially damaging. If we're talking about upper limbs, it's a flexor reflex. If it involves lower limbs, it's a cross extensor reflex. Here, if the right hand touches something painful, something damaging, signals come in through that nociceptor, which is a pain fiber. It innervates an interneuron, an excitatory interneuron, and there's no pluses and minuses, so how do I know this one's excitatory and this one's inhibitory? The solid lines, excitatory, the dashed lines, inhibitory. So you have to know how to read these. So we excite the sensory neuron, it's a nociceptor. It in turn excites an interneuron, which in turn excites a motor neuron that goes to a flexor. Because you had to extend to put your hand on the sharp object or the hot stove top, so you need flexors to withdraw. And of course, if you're going to stimulate the flexor to contract, what are you going to want the antagonist is doing? You want to make sure it's completely relaxed, so you're going to inhibit it. So that excitatory interneuron synapses onto an inhibitory interneuron, which then inhibits the motor neuron going to the antagonistic muscle. Again, 2 limbs to the reflex. If it involves the lower limbs, it increases the level of difficulty because now, not only do you have to take your foot off of that sharp or hot object, but you have to maintain balance with the other limb. So now both limbs are involved. Cross extensor because opposite the side where we activate the flexors to withdraw, we have to activate the extensors to maintain body position. So right foot goes down on the sharp object. Nociceptors are excited. Pain signals come in to the spinal cord. Pain signals come into the spinal cord. So we activate, what are we going to do? No, we can do this. So here's an excitatory interneuron, which excites these motor neurons. This motor neuron goes to the flexors on the ipsilateral side of the stimulus, which makes sense, right? It's the right foot that stepped down. It's the right foot that needs to be pulled up. We need flexion at the knee and flexion at the hip to do that. And we're just looking at the knee muscles here. At the same time you stimulate the knee flexors, you want to make sure you inhibit the knee extensors. So the nociceptor activates an excitatory interneuron, which synapses onto an inhibitory interneuron, which inhibits the motor neuron going to the antagonistic muscle. Then we have to deal with the other side. The opposite limb, the contralateral limb, is going to have to maintain balance of the body. So we have to make sure that this knee remains extended. So the excitatory interneuron that was excited by the nociceptor is going to synapse directly onto the motor neurons on the opposite limb. They go to the extensors. And then that same inhibitory interneuron that was excited by the excitatory interneuron is going to inhibit the flexors. 4 limbs to this reflex, right? 2 for the right lower limb and 2 for the left lower limb. We have to make sure that while we stimulate the agonists, we inhibit the antagonists. Same reflex, but this is from our textbook, and this one is from a different textbook. All right, so you have a handout with a bunch of page numbers and empty spaces to write something in. Those are the cranial nerve tests. We're gonna do a virtual version of those tests, just kind of talk through it. If you have your lab manual, you can follow along. It starts on page 371, and I'll read it out to you guys. A component of every complete physical examination performed by a healthcare professional is the cranial nerve exam. In this exercise, you will put on your doctor hat and perform the same tests of the cranial nerves done during a physical examination. Pair up with another student. Take turns performing the following tests. For each test, first document your observations. In many cases, this will be able to perform or unable to perform. Then state which cranial nerves you have checked with each test. Keep in mind that some tests check more than one cranial nerve. Some cranial nerves are tested more than once. But each nerve is tested in this exercise at least once. When you have completed the activity, answer the check your understanding questions at the end of the unit. Number 1, have your partner perform the following actions individually, not all at once, and you'll see why. Smile, frown, raise eyebrows, puff cheeks. Smile, frown, raise eyebrows, puff cheeks. So what cranial nerve or nerves are you testing?
Facial.
Yeah. Because the facial nerve controls the muscles of facial expression. Smile, frown, raising eyebrows, those are all facial expressions. Number 2, have your partner open and close the jaw and clench the teeth. Chewing muscle. Trigeminal. Trigeminal controls chewing muscles. Are you checking the motor or sensory component of trigeminal?
Motor.
Number 3, have your partner elevate and depress their shoulders and turn head left and right. Upper traps, sternocleidomastoid, so that must be accessory, cranial nerve 11. Draw a large imaginary Z in the air with your finger. Have your partner follow your finger with their eyes without moving their head. Repeat, but next time do an H. Cranial nerves tested. Oculomotor, optic, because you can't follow if you can't see, so optics involved for sure, for sensory, but oculomotor for motor. Abducens, trochlear. So all 3 muscles that control the extrinsic eye, all 3 nerves that control the extrinsic eye muscles. So oculomotor, trochlear, abducens, plus optic, right? So 4 are being tested altogether. What if the only thing the person can't do is look laterally? What nerve might be an issue?
Abducens.
Abducens. Number 5, it's a pupillary response. So we're going to shine a pen light into each eye. See what happens to the pupil when we shine the light into the eye, and then when we pull the light away. And then also we're going to put a hand right over the bridge of the nose to make sure when we shine the light into the left eye, it's not being shone into the right at the same time. But what you're going to see is when the left pupil constricts, so will the right. It's a consensual light reflex. So, what are you testing?
Pearl,
Pearl.
optic.
So this is number 5.
Where's optic?
No, no.
Well, optics involved, right? Because there's no information regarding light reaching the central nervous system without the optic nerve. But that's not the main one we're testing, but yeah, it's involved, you could write it. You could write down optic, that's one. What's the main one we're testing? What actually controls the pupil, makes it constrict and dilate? The iris, intrinsic eye muscle. Which cranial nerve controls intrinsic eye muscles?
Oculomotor.
Oculomotor. So we're testing 2 and 3. Number 6, have your partner focus on an object on the far side of the room for 1 minute. Then have your partner switch focus to an object in your hand. Watch your partner's pupils carefully as the point of focus is changed from far to near. Intrinsic eye muscles again.
Oculomotor.
Oculomotor and
Optic.
optic. So you have intrinsic eye muscles that change the diameter of the pupil, and intrinsic eye muscles that change the shape of the lens for focus. Number 7, have your partner swallow and speak with your hand placed on their throat. Feel for symmetrical movement of the larynx.
Glossopharyngeal.
Glossopharyngeal and vagus. What do they have in common? They both innervate the pharynx, but vagus also innervates
Larynx.
larynx. Number 8, have your partner protrude their tongue. Check for abnormal deviation or movement. For example, does the tongue move straight forward or does it shift off to one side?
Hypoglossal.
Hypoglossal. So what if it shifts to one side? They can't stick it out straight, it just goes to one side.
Broke.
One of the hypoglossal nerves might be good, the other one might be defective. All of these cranial nerves are bilateral,
That's why you get
right? There's a left and a right. So if the left one is working, and let's assume crossing over occurs, then you're going to contract the muscles on the right side of the tongue. And if the right one is working, you'll control the muscles on the left side of the tongue. But if only one is working, the tongue's going to go off to the side. Number 9.
That's a stalemate.
In order to test vision, have your partner stand 20 feet from a Snellen chart. So on the left of the screen on the wall is the Snellen chart. And read the chart starting with the largest line and stopping with the smallest line that your partner can read clearly. Record the ratio, for example, 20/30 next to the smallest line. What are we testing?
Optic.
Optic. Number 10, hold a tuning fork by its handle, strike the tines with a rubber mallet, or you can just tap it on the desk, on a tabletop. So now the tines are vibrating. You place the tuning fork right on the mid-sagittal line, right in the center of the skull, and then you ask the subject, do they hear the sound that that creates equally on both sides, or is it louder on one side or the other? Vestibulocochlear. And if it's louder on one side than the other, then maybe one of the vestibulocochlear nerves is damaged. Number 11, have your partner stand with eyes closed, arms at their sides, and stand there like that for several seconds. Upright, hands to the sides, eyes closed. Vestibulocochlear. But this time you're not checking the cochlear component, you're checking the vestibular nerve component, the vestibular apparatus. And if they can't maintain balance, that doesn't automatically mean there's something wrong with the vestibulocochlear nerve. It just gives you a starting point, right? Because the nerve could be totally fine, maybe it's the vestibular apparatus that's the problem. Or maybe it's the vestibular nucleus in the brainstem that's receiving those signals that's the problem. Doesn't necessarily mean it's the nerve. But if the test is positive, meaning they perform everything correctly, then what you can say is the nerve's good, right? Everything's good. Number 12, hold an unknown sample near your partner's nose and fan the odor by waving your hand over the container. So we have all these containers. We have stuff to do all the sensory testing in the cabinets on down below next to the hood. You can play around with those sometime. But we have olfactants, we have tastants, we have the tuning fork, we have the rubber mallet to do all this stuff. Although you can do almost all of this at home if you wanted to. Just get anything that has some odor to it, and, maybe a little jar of cinnamon or something, and kind of do that kind of thing. And what are you testing? With these various olfactants.
Bottle absorbing.
Cranial nerve what? One. Olfactory. Number 13, evaluate your partner's ability to taste by having your partner place a piece of PTC paper on their tongue. The ability to taste PTC is genetically determined. About half of the population can taste it. If your partner cannot taste the PTC, try the thiourea paper instead. A word of warning, thiourea tastes bad. If your partner cannot taste either of these papers, send them to the ER.
Oh.
No, it says try sodium benzoate paper instead. So what are we checking?
Vegas.
Vegas? Nope, not at all. Vegas does not innervate the tongue. We are putting these papers on the tongue. So
Or are you
glossopharyngeal
looking at
and
epiglottal?
facial. Which of those two innervates the anterior 2/3 of the tongue?
9, 10, 11.
Facial.
Facial. And the posterior 1/3 of the tongue?
Glossopharyngeal.
Glossopharyngeal. Vagus provides taste, but from what?
Epiglottis.
The epiglottis, not the tongue.
Why did it say send them to the ER?
That was because they got issues.
Oh.
Because
What it really said was try the sodium benzoate paper.
because by then you're pretty sure they have a
We made it.
Said try a tomato.
All we have left is chapter 14, which is only 3 pages. Should not take more than an hour, so I'll have lots of lab time on Thursday. Make sure all of those new structures that we covered today, spend time with them at home before you come in on Thursday and work with the models. Otherwise, you'll need to spend the entire time on one model if you're going to try to learn it from scratch.
That's what I do. Always.
Yeah. It's typically the vestibular apparatus. It happened to my wife recently, and the doctor described it as crystals are loose and just moving around in the fluid. And there's these exercises that we're having her do to try to get it back in the right position. It's fairly common. Sometimes it lasts a day or two. In the case of my wife, it was like 6 weeks. And at first it was horrible. She was getting nauseous. She had to hold on to things when she was walking around. Just the crystal coming loose. Just happens randomly sometimes. Yep.
We test all those things when we test for concussions.
I thought
It's a big deal.
it happened to me like 5 years ago, and I thought I was having a stroke. I literally was.
It was
Like,
vertigo?
yeah.
I'm
Yeah.
thankful I haven't had it, because the worst thing in the world to me is being nauseous. I absolutely hate that feeling. It's what keeps me from drinking too much. Nothing worse than a hangover where you're just throwing up and spinning and nauseous. Keeps me from drinking too much. I hate being nauseous. Absolutely hate it.
You know what keeps me from drinking?
Nausea? Just the effect of alcohol on the brainstem, on the vomiting center.
So then all those beers are good for you.
Really, your body is doing what it's supposed to when there's a toxin present, right? Your body is throwing off
Yeah, I did, thank you.
Looking too well? Yes.
I probably get like the